So, so we saw, right, optical flow, we saw that there was this Lucas-Canaday method, right, that can deal with large shifts, and then there was one for a small shift, and then we had a variant for that which could handle large shifts and so on. And therefore, it automatically there's a lot of interest, right, in terms of having deep networks that can save this, that can solve the same problem. And right, I'm going to talk about one or two most sort of relevant works. This is a 2015 paper. By the way, I mean, right, both these works, right, which I'm actually talking about are roughly by the same bunch of authors, just one or two have changed, but really, right. So, and one of them is actually Thomas Brock's, who has done some very good work in optical flow in terms of classical method before. So, it's not surprising that he took the plunge and came into the deep network domain to see what he could contribute there, right. So, you see this, there is a flow net S and then flow net C. So, S typically stands for simple and then C is for actually complex, but C is also a correlation kind of flow net, and you can also think about C as core or flow net core, sometimes it is written, or flow net C. So, the way this works is actually it is completely supervised, okay, and you might ask, right, how does one do optical flow in a supervised way. So, the way they actually do is they actually created a flying chairs sort of a data set. And what that meant is, they kind of assumed a chair right inside a room, and then they would apply affine motions, different kinds of affine motions, independent affine motions on the independent, because you are kind of thinking of a camera moving around and then the objects flying around. That's why it's called flying chairs, right. So, they apply a different affine motion on the chair, a different affine motion on the scene, and then because they know exactly what, and then because they have a 3D model, right. So, they can tell exactly where what is going. In fact, that is what it is one of their sort of main the contributions. Other than the network and so on, even to create a data set like that where you can handle occlusions, because what happens is when you actually apply an affine motion, right, what will happen is something that this fellow was hiding before it will start to appear in the next frame because you moved, but then what was originally appearing here will start to not, you won't see in the next one, right. So, they kind of take care of all of that. So, they kind of handled all of that, and that is why, right, it's called I think these days they call it the chairs data set. And it's actually pretty simple, right. And one of the things that you want to do is this kind of a downsampling. So, they have something like a contraction part which is up to this, okay. This entire thing is kind of a contraction, and then there is actually a refinement which is the expansion part. And why do they want to do contraction expansion? Same thing, right. You want to be able to, one is you don't want to kind of take the high resolution image all the way inside, okay, because computationally it's going to be costly. Second thing is that you want to be able to get aggregate, you want to aggregate, right, what is around, right, in terms of the context. So, the context, right, you want to get as much context as you can, and that is one of the reasons why you downsample, right. Of course, you can do convolution max pooling, right, which is what they do, okay. So, like a con max pool, but then this is one of the original papers. So, what they did was, right, when they came to that sort of end of that contraction part, right, they had to go back to the original image size, because optical flow is exactly the same size as the image, and then you have to find out what is u comma v for every one of those pixels. You have the ground truth with you, but then it has to actually predict at that higher resolution, because you have come down in terms of resolution. So, this refinement part, right, they did something, right. So, this refinement part, right, actually looks like this. So, what they do is in the refinement, so the last layer, right, that kind of comes from the downsampling sort of blocks. So, what they will do is, so they have so what they do is if you simply interpolate that, right, back to the original size, it will look very smoothed out, right, it won't look nice. So, what they do is they actually take the input, or take the output of the next previous convolution block. So, it is like con phi must have been the earlier one, then con 4 is even earlier, than con 3, and then all the way to the input, right. That is how you have to think about this. So, what they do is they actually upsample this con 6 by a factor of 2, because they know that they come down by a factor of 2, which means that it will match the dimensions of con phi output, and then they will actually fuse the 2, then go to the next level, and then where they will bring in con 4, because con 4 will then match the size of the output here, right. So, that will match the size of the output here, and then right, you go like this, and so on, and then right, eventually hit the highest resolution, which in this case is some, say 96 cross 128 or whatever, and that is where you actually do that is how you do this refinement. Then they had also this other network, right, in the same paper, which they called as flow net core. Now, if you look at here, the input was stacked, right, in the sense that both the input frames for which you want to compute the optical flow, they were stacked together and sent. Whereas in flow net core or flow net C, right, what they did was they had actually identical sort of arms, okay, in both, in the sense that they wanted to pick up feature maps that are independently that you can independently get for each image. Okay, then they had a correlation they have a correlation block here, which is actually which you don't have to train. It's a usual correlation, and this correlation is done right among the patches. I mean, so you have these two feature maps, right, coming out of the left and the right, not left and right, the first and the second frame, and then they would actually look for the correlation among the patches, right, as a function of how far away are they from each other, and that correlation information then they pass through this kind of a flow net S. I mean, after this, whatever follows is roughly the same as what they had earlier. The claim was that using this correlation actually helps you to improve the optical flow. Again, right, these are, I mean, deep networks, as we always say, right, it's very hard to sort of pin it down to exactly, unlike the analytical approaches, right, where the insight is way higher, right, than you can get out of a deep net. But yeah, that's how, right, people, the idea in deep networks is to be able to come up with something that works. So why you did that, and then as long as you have something reasonable, some reasonable explanation going, right, people accept it. And right, so here is that kind of a synthetic sort of a data set, which is called the chairs data set. Of course, some of those look very unrealistic, because you don't have a chair, right, flying around across a building and so on, but then they could do that because it was all simulated, and then right, so they had some augmentations and so on, and then the kind of then this is the optical flow, which is actually a color coded optical flow. Then they also compared it with some epic flow and so on. And then they had a following network. It was in 2017. This was called FlowNet 2. The earlier version was like FlowNet 1, and here the main thing was this, right. So they wanted to handle large shifts. The earlier one could only handle small shifts, so they wanted to build something that can do larger shifts, right, across the two frames. Similarly, following just like what we did for Lucas Canaday, we said for small distant displacements first, and then how do we handle larger displacement. Same line of thought, but now what you see is, right, they have a FlowNet C followed by a FlowNet S followed by FlowNet S, and there is another network here which is meant for small shifts alone. So what they do is, so they again, right, FlowNet C, as you know, right, takes actually two of them into independent arms. That's how it takes it. Whereas FlowNet S, we know that it takes a concatenated set of feature maps, except that it's modified a little bit in order to take the warped version of image 2, then image 1, then the optical flow computed out of this large sort of a displacement network, and then they also take the brightness error. So the entire thing is kind of given as a concatenated set of feature maps to this FlowNet S, which in turn kind of predicts a flow, which flow is then used to warp image 2. So the idea is that as you keep right going inside, the optical flow sort of a difference will reduce, right. That means optical flow vector will itself go down in value, because you're already warping and sending, and then the idea is that and then this network, right, that they have here, this is SD, means small sort of a displacement. There, what they say is that, I mean, if in reality, if your frames did not have a large displacement, then having this helps, in the sense that because these are meant for large displacements, but then this one, right, it doesn't influence anything if there is a large displacement, but then when there is a small sort of a displacement, then they say having this helps in addition, right. It doesn't have any influence when there is a large displacement, but for small displacements it's useful. Then finally, right, the features coming out of this are fused with the features coming out of the FlowNet SD, and then you get the final flow, it's completely supervised. There are a couple of works, that are unsupervised, but then, right, I'm not even going to unsupervised things, because those are there's still a long way to go there. Okay, so even supervised networks are still struggling. Okay, and here are some more kind of results, and then you can kind of take a kind of look at this paper, right, for those of you who are interested. And then mainly, right, you have to kind of look at the time also, because when optical flow you want things to run in a real time, so you're looking at milliseconds, right. So FlowNet 2 takes a little bit more, but then you can see that, right, the way it comes out with the movement, it's very nice. Right. So the ground truth, look at this and look at this, right, whereas these are still struggling. PCA et al is way away, and this one is way away in time. So all of that matters, right, time, architecture, the parameters, the accuracy, and so many things. Now as far as semantic segmentation is concerned, right, so by segmentation what do we mean, right, I mean, we really mean by semantic segmentation we want to classify objects, right, I mean in the scene. So in this case, right, we want to give kind of, right, one label to the tree and then a label to the road, right. I mean, so here is an automatic driving car or something, and then what it is seeing, right, in front of it, right, seeing all. So you have segmented the people out, and then you have segmented whatever, right, the road out and so on, right. This is what you want to do, okay, ideally. And of course, you can kind of go back to all those segmentation techniques that we talked about, but then really if you wanted to do it with kind of a deep network, then what it means is, right, you want to be able to label every sort of a pixel with a class label now, right. I mean, this is not like a recognition or a kind of a classification problem. right. Here it's a kind of classification, but at the level that every pixel you have to tell, right, which label it should belong to. So you already have an idea, right. Let's say you've got some, say, right, no, 10 classes or something, and then every sort of a pixel in the image you want to tell, did it come from class 1 or class 2 or something, and then once you do that, right, then you have a segmentation map. Now the deep networks, right, that have been around, right, are somewhat like this. So the initial works were on FCNs, which are fully convolutional. And again, right, the same idea, this kind of downsample and then upsample, this all goes back to the same argument that in terms of the resolution, right, you don't want to be operating at a high sort of a resolution, one thing, right, because then it makes it computationally expensive. Then second thing is in terms of the, so one of the things is the see, what do you call it, see, a receptive field, right. This is very important. So you want a receptive field that is actually very high, right, because you need context. So for example, if you see a tree and then, right, if you see in the context that there is a road next to it, then that you want to get a pick up, right, so that next time you see an image with a tree, then there is a context, right, that you have learned before, that a tree, right, possibly appears with a road somewhere around it or with some soil around it. Right, all of that is what we mean by the context, right, or if there is a person, then maybe, right, very likely that that somebody is typically next to him, or for example, if you are inside a room, then maybe, right, there could be a table. So all these things are actually, right, we are not right, we don't kind of directly teach, right, explicitly, but then implicitly, right, it is supposed to learn, and the only way it can learn is by kind of looking at the whole thing. When it wants to segment a pixel, it should also be looking at the kind of global sort of a context, right. If it looks very locally, right, then it's going to miss out on whatever else that is around it, which can actually aid in the, say, segmentation task, right. So that is the reason why you typically have this kind of downsampling layers. And then of course, one of the things that you should remember is that how do you think your final layer will be like? I mean, suppose I do this, right, I do some convolution, I do some downsampling, right, I do some max pooling and all, then again go back to the original resolution, because the segmentation has to come at the original image resolution, right. Now how do you think will that final layer look like now? I mean, when you did the classification and all, right, there was a certain way in which you did it, right. Here also it's a classification problem, but then it's actually a per pixel classification. So how would your output layer look like?
2D kind of.
It'll be actually a 3D. I mean, not 2D. It'll be a volume. See, if it's 2D, right, then it's just one plane, one feature map, a 2D feature map. But in that pixel, in that every pixel, you want to be able to tell which class it belongs to, right? So if you have just one, you can't do that, right? So you will have multiple. So how many? As many as the number of classes. Right, as many. So if you have 10 classes, you'll have 10 feature maps, and for every pixel you will say, with what sort of a probability, right? Could that be in class 1? Then what is the probability that it is in class 2, class 3, and so on, and that you would do for every pixel. So when you do a cross entropy loss, or for example, when you even do the softmax, it will be a per pixel softmax now. Along the depth, right? It will be a per pixel softmax now. Right? Earlier we had only this one, right? We had a situation where we had only one vector, right? It was like a one dimensional case. Now you have, like, right, vectors all over the place. So you have to do a per pixel softmax followed by a per pixel C across entropy, because for that vector, right, you'll have a one shot, right? You'll have for that particular pixel, you'll have a one shot vector as a ground truth, which will say that 0 0 0, and then, oh, this is that class, right, to which it should belong, 1 0 0 0. That is your y, right, yi. Right, and then you have a y hat, right, which is what is the network's output, and you do that, whatever, right, minus summation yi log yi hat, right, and that is your cross entropy, but it will be at a pixel level. So this you need to do for every this one pixel, and you simply average these losses. But normally what is done is, right, people compute what is called, in order to find the accuracy, right, people compute what is called the mean intersection of union. So it's like saying that, right. So it's like mean is just the average over all classes. But for one class, right, imagine that the intersection over union is like A intersection B over A, say, union B. So what this means is that A is really a target, which means that I know, for example, which of these pixels are supposed to be from that class. B is actually a predicted output. So what it is saying is, ideally IOE should be 1. In the sense that A intersection B should be equal to A union B. If not, right, it will start to reduce. If you are doing very badly, then IO is going to be close to 0. right, and mean IOE means over all the classes we need to kind of do this, right. That's kind of a way to kind of compute the accuracy, because you can't do like mean square error and all here, right. That doesn't make sense. I mean, if you want to know how well did I do overall, I completed the training. Yeah, right. I have completed my training and I need to know how well did I do. So the way to, so that metric that they use for segmentation is what is called mean intersection over union value. And here, right, and as you see, right, it kind of goes down, and then afterwards, right, again, of course, you need to do kind of some kind of an upsampling, and which these fellows. So how the upsample is again somewhat similar to what we saw in the optical flow paper, right. So what they will do is, so you have come down all the way to kind of pool phi, right. This is like max pooling layer, and then after pool phi, what they will do is, so one of the things will be like a full blown 32x, right, which is your final resolution, okay. And then what they will do is they will then scale this up by in the, okay, where is this 2x upsampled and 16x, 1 minute. Okay. So what they will do is, so for example, right, so here right, this map, right, you actually upsample it by 2x, and then you actually fuse it with this is the pool 4 layer, which will have the same sort of a resolution as this upsampled output. This is what you saw in the optical flow also, right, which means that the output is now 16x upsampled, and then right, this one you take and then upsample it by actually 2x, and that output, right, will come from here. So from this pool 3, right, you will take this, you will actually fuse it, because these two are at the same sort of resolution, and then right, I mean, that's how you go, right, in order to be able to arrive at the final sort of a segmentation map, which you will compare with this on ground truth. So this is called the skip layer concept. This is not the best way to do things. Okay, I think this must have probably come from the idea of the way, right, in optical flow papers, right, the way they did it. I do not know which one came first and which one came later, but the ideas look very similar. So what happens is, right, so if you do one skip connection, then right, it's not so good. So 2 skip means you are going further back. 3 skip will mean you will go further back and then integrate information from those pooling layers. And the ground truth, of course, so you can see that this is still not so good, right, because you have still not got the hands and all properly segmented. There is a lot of smoothing going on, right, because you have lost this detail here, you have lost some details here and there, right. So not a great output, but yeah, at that time I think it was still considered good. Now then came this kind of a deconvolution network.